Well, ever since I've been looking at evidence for creation and for general pointing to God that we see in Romans 1, I've been convinced that two kinds of people absolutely should be creationists, and that's doctors and astronauts. Because if you know enough about biology, or if you know enough about outer space and orbits and the celestial makeup, you cannot be objectively an atheist. Many are, and they are ignoring some of the evidence. And tonight I'm going to take you literally out of this world into a realm that we don't think about much. I'm going to try and expand your mind. If you're already expanded, I hope to enrich your mind. But this is an argument that I've been working on for a long time. Someday I'll write it up into a convincing format that is publishable, but for now you're going to get to hear the argument in its developed form but not polished form. So this should be fun. So we're going to start, as we have been starting, with a story, a narrative, and it has to do with my dad. But we're going to start even farther back than my dad. This is General Billy Mitchell. He was one of the highest decorated aviators in World War I. He basically was part of the leading aviators that developed air power. And so he became an air power advocate to the extent that he was an embarrassment to the Army generals that didn't really want air power to be that successful. And so he, by 1925, just less than 10 years after the war, he had been advocating openly for air power and was court-martialed because he was not towing the party line. So he ends his career in somewhat of a disgraceful way. He's court-martialed. But just 6 years later, 1931, there was an event that my dad told me about, and I'd never heard about it before, so I did some research. And what happened was, in 1931, some other air power advocates decided that they needed to stage a demonstration of what air power could do. And so they amassed the largest fleet of aircraft ever assembled, and they basically flew it over New York City as if it were an attack. They had lots of publicity, people knew that it was coming, and so thousands of people were out to watch. And among those thousands of people, my dad skipped school. Now, he was born in 1917, this is 1931, so he would have been about 14 at the time. And his parents were deaf and mute. And so he got away with murder. We found out later from my aunt that he was a bit of a troublemaker. Never too bad, but anyway, so he skipped school to go out to this event. And what he told us was, it would have gone great, except there was an aircraft that had a landing gear collapse. And so he told us this story in his late 80s. We'd never heard about it before then. But he tells us this story that this aircraft had a gear collapse and nobody was hurt. They were relatively, again, I don't know if they were uninjured, but they walked away. And so he is out there at the field and he goes out to the airplane next to the airplane with the gear collapse and is looking in the cockpit, and a news reporter takes his picture. And it's on the front page of the paper the next day. So he tells me this story, and like a typical historian, I want to validate this, right? And so I had a number of layovers in New York City where I went to New York Public Libraries, a New York newspaper. I said, I got to get a copy of this if it exists. So I got the dates kind of refined and figured out when the event had happened. And I started looking, and I just couldn't find the newspaper. It was kind of a newspaper that had gone out of business. Well, found out the archives that keep it, the microfilm is all at the Library of Congress. Okay, so my next couple of Washington, D.C. layovers with the airline, I go to the Library of Congress. And I start looking through all this microfilm. And I found this. 600 plane armada swoops into the city on the eve of theoretical battle in the clouds. And here's this airplane with a guy looking in the cockpit. And the big question for us is that him? Hard to say. The microfilm does a pretty good job of capturing the text, but it doesn't do a very good job of capturing images. And so the image is a bit grainy. So we don't know for sure if this is my dad, but it's at least circumstantial evidence that he was once again telling the truth. And there's at least, so we have this digital copy of what we think was probably my dad. So the tie-in to astronomy is this. When he was nearing the end of high school, he told his parents that he really wanted to do either, he wanted to be a pilot or he wanted to study astronomy. And they were having none of it. They told him there was no future in either one of those. And they made him drop out of school about 3 months before graduation. So he never graduated from high school. And we didn't find that out until he was 85 years old. He died at 88. Probably something that he had harbored all of his life, and it had grated on him. You just think about that, and how my dad was a traveling salesman. He did fine, but he was a literate, he was an eloquent man. He was gracious. He had great penmanship. He was a good writer. Think of what could have been different had they allowed him to pursue his dreams. Turns out aviation and astronomy both turned into pretty good fields, right? So tonight we're not going to look at aviation, but we will look at astronomy. One of his loves that inadvertently he passed on to me, I guess, in some respects. So tonight what we're going to do is we'll look a little bit at what God says about the constellations, stars, planets, and moons. We'll look at where we are in the universe. We'll look at the necessary conditions that make orbits and the solar system work, and then we'll focus most of our time on the solar system itself and see how it works and whether it in fact does provide a case for design. So let's look at Psalm 8. O Lord, our Lord, how majestic is your name in all the earth. You have set your glory above the heavens. When I consider your heavens, the work of your hands, the moon and stars which you have set in place, what is man that you are mindful of him, the son of man that you care for him? Yet you have made him a little lower than the heavenly beings and crowned him with glory and honor. That's the verse that you had, obviously, in the video that we showed just a minute ago. And the rest of it goes like this. You made him ruler over the works of your hands. You put everything under his feet, all flocks and herds, beasts of the field, birds of the air, fish of the sea that swim the paths of the seas. That's all the stuff we studied last week, right? O Lord, our Lord, how majestic is your name in all the earth. And when you look at this passage, there are a number of references, of course, to last week, but also to this week. The heavens are referenced a couple of times, the moon, the stars. So we see a number of references to the astronomy that God is really proud of. In Scripture, in fact, there's a lot of references to these astronomical entities. We have the sun 61 times, the moon 144 times, and the stars 55 times. Now, sometimes there are general references to don't worship them. So they're not all references to magnifying God's name in an appropriate way. But the point is that they're prominently involved in the Scriptures. Psalm 147:4, he determines the number of the stars. He gives to all of them their names. When I started studying this a little more seriously, maybe 20 years ago, there were about 200 billion galaxies, and there were about 100 to 200 billion stars in each galaxy. I can't keep up with the numbers, but now they're saying there are probably 1 trillion galaxies. I mean, every time you look at it, the number grows. And you're probably familiar with this. You've seen this in your lifetime as well. Planets, there's no specific references to the planets, but they would have looked like stars to the observers back then. So that kind of makes sense. Constellations actually appear quite a bit. Not a huge amount, but there are some references to the Great Bear, to Orion, the Pleiades. Those show up a couple of times. There's the Chambers of the South, which is probably a constellation. The Crooked Serpent is probably also a constellation. There's in the Chinese pantheon of the constellations, there's a great dragon, which probably appears in the book of Revelation. And that's another talk. We won't get there. But when we talk about the Star of Bethlehem, that the constellation that's involved in Revelation 12, I think is prominent. So these constellations are used by God to tell a story. There was one story, in fact, well, we won't get that's a tangent. I'd love to go down, but we'll just skip that. Anyway, so let's talk about the necessary conditions for our physical lives to exist. Okay, so we're going to talk about the four fundamental forces in nature. And the first one we're going to talk about is light. all seen this cute image, a lamp, and the lamp is emitting light, right? There's a couple ways that we can foster light waves, light particles. So for you engineers in here, what is light? That's a great definition.
Absence of darkness.
Absence of darkness, okay, that's a negative description, but that's good. The point is, we don't really know. We know that it has the characteristics of both waves and particles. It's a dual nature description that we've given to light, but we don't really know exactly what it is. We can describe a lot of characteristics, but exactly what it is a little bit difficult to pin down. So should we leave light on the table for now? Okay, let's go to the next one. That's another easy one, gravity.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
So I don't know if any of you are old enough to remember when that happened. It was 1971. I didn't see it live. I was in basic training and didn't have access to television at that point. But this experiment that was proposed by Galileo has been repeated by NASA, both on the moon and in vacuum chambers, just for demonstration purposes. Gravity acts in a predictable way, but again, I would ask, what is gravity? When Newton proposed his laws of gravitation, he was widely mocked because they knew you couldn't have force at a distance. And this force at a distance became a real argument against the way he described gravity. And that's what some of the medieval science revolution guys started calling ether. They figured there must be something out there. It's kind of like we propose dark matter now because we don't know what else to use to describe the forces we can't quantify in any other way. But in fact, gravity acts in a complete vacuum without any physical connection between bodies. We don't know why that is. We have lots of good ways to describe it, and we'll describe some of the things it does with orbital systems today. But exactly what it is, we don't know. The more mass a planet or a sun has, the stronger the gravity is. We know how to measure those things. So lots of descriptors, but what the real nature of it is anybody's guess. Okay, let's go to some other easy ones. This is a carbon atom. A carbon atom has 6 neutrons, no charge, and 6 protons, positive charge, and they are all in the nucleus. What holds together these protons that should be repelling each other because they all have a positive charge? We don't know, but that's the strong force of the atom. And I'm probably oversimplifying it for people like Craig that really understand this stuff. But the subparticles, the protons and neutrons are made up of quarks and Higgs bosons and a bunch of other things that I can't understand that theoretically we've determined probably exist, but we can't see them. They're too small, obviously. Well, around this thing, we have electrons. And in this case, there are 2 in an inner quantum shell, and there are 4 in an outer quantum shell. The next shell out can hold 8. So this makes it a very reactive, essential chemical for life because it bonds so well with all the things that life needs. So if you were to grab any of these particles, take your pick. It could be an electron, could be a proton, could be a neutron, could be a Higgs boson or a quark. If you were to go to the farthest distance at the edge of the universe, which probably doesn't exist, but if you were to go there and grab an electron at the farthest possible point and bring it back to Earth, what would it look like? All the other electrons. Think about the quality control to make all of the subatomic particles exactly the same. That's a miracle right there. So the strong force holds the particles that should repel each other together. The weak force holds the electrons in their orbits. Do I have that right, Craig? Okay, that's good. But again, what keeps the electrons from just being sucked into the nucleus of the atom? They have very little mass. They do seem to have some mass, and they're held in an extremely high velocity orbit, we think. If you look at them, they're in the wrong place. There's a thing called Schrodinger's rule that says if you observe it, it's different than where it was before. And there's just nothing makes sense at the quantum level, but all of it made sense to God because He made it all. So we could quit right here. You can go home and think about that for the week, but we're going to keep going. All right, so what I want to do next is talk about not just these forces, but how finely they are tuned to work together. Okay? If they were off just a smidge, which I can't define small enough, nothing would work. So this little video shows that pretty well.
From galaxies and stars, down to atoms and subatomic particles, the very structure of our universe is determined by these numbers. These are the fundamental constants and quantities of the universe. Scientists have come to the shocking realization that each of these numbers has been carefully dialed to an astonishingly precise value, a value that falls within an exceedingly narrow, life-permitting range. If any one of these numbers were altered by even a hair's breadth, no physical, interactive life of any kind could exist anywhere. There'd be no stars, no life, no planets, no chemistry. Consider gravity, for example. The force of gravity is determined by the gravitational constant. If this constant varied by just 1 in 10 to the 60th parts, none of us would exist. To understand how exceedingly narrow this life-permitting range is, imagine a dial divided into 10 to the 60th increments. To get a handle on how many tiny points on the dial this is, compare it to the number of cells in your body, or the number of seconds that have ticked by since time began. If the gravitational constant had been out of tune by just one of these infinitesimally small increments, the universe would either have expanded and thinned out so rapidly that no stars could form and life couldn't exist, or it would have collapsed back on itself with the same result: no stars, no planets, and no life. Or consider the expansion rate of the universe. This is driven by the cosmological constant. A change in its value by a mere 1 part in 10 to the 120th parts would cause the universe to expand too rapidly or too slowly. In either case, the universe would again be life-prohibiting. Or another example of fine-tuning. If the mass and energy of the early universe were not evenly distributed to an incomprehensible precision of 1 part in 10 to the 10 to the 123rd, the universe would be hostile to life of any kind. The fact is, our universe permits physical, interactive life only because these, and many other numbers, have been independently and exquisitely balanced on a razor's edge. Wherever physicists look, they see examples of fine-tuning. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. If anyone claims not to be surprised by the special features that the universe has, he's hiding his head in the sand. These special features are surprising and unlikely. What is the best explanation for this astounding phenomenon? There are 3 live options. The fine-tuning of the universe is due to either physical necessity, chance, or design. Which of these options is the most plausible? According to this alternative, the universe must be life-permitting. The precise values of these constants and quantities could not be otherwise. But is this plausible? Is a life-prohibiting universe impossible? Far from it. It's not only possible, it's far more likely than a life-permitting universe. The constants and quantities are not determined by the laws of nature. There's no reason or evidence to suggest that fine-tuning is necessary. How about chance? Did we just get really, 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 really lucky? No. the probabilities involved are so ridiculously remote as to put the fine-tuning well beyond the reach of chance. So, in an effort to keep this option alive, some have gone beyond empirical science and opted for a more speculative approach, known as the multiverse. They imagine a universe generator that cranks out such a vast number of universes that, odds are, life-permitting universes will eventually pop out. However, there's no scientific evidence for the existence of this multiverse. It cannot be detected, observed, measured, or proved. And the universe generator itself would require an enormous amount of fine-tuning. Furthermore, small patches of order are far more probable than big ones. So the most probable observable universe would be a small one, inhabited by a single, simple observer. But what we actually observe is the very thing that we should least expect: a vast, spectacularly complex, highly ordered universe, inhabited by billions of other observers. So even if the multiverse existed, which is a moot point, it wouldn't do anything to explain the fine-tuning. Given the implausibility of physical necessity or chance, the best explanation for why the universe is fine-tuned for life may very well be it was designed that way. A common-sense interpretation of the facts suggests that a super-intellect monkeyed with physics, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question. There is for me powerful evidence that there is something going on behind it all. It seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming. The heavens declare the glory of God. The skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they reveal knowledge.
So once again, we see a mind-boggling array of impossibilities that we have to get behind, to have to get beyond those in order to explain life, and design ends up being the best explanation. There are a couple of other necessary conditions, so let's look at those. One that I hadn't thought about before, but Jason mentioned, we talked about it this morning, is this, and that is time. What is time? We have a sequenced chronological order of events, but we have a sequence of events which we measure chronologically. What is time? We measure it, but we can't compress it, we can't expand it, we can't manipulate it in any way, shape, or form. We have tools, we have calendars, we have hourglasses, we have timelines, we have clocks that all help us live within time, but they don't explain time. So let's look at our place. Any questions on the that's kind of the end of the forces part that I think is really important to put in place before we get too far. Everybody good with that? All right. Let's move on to where are we? So this is kind of a funny little intro video, but it does explain pretty well the problem of what is the universe.
On, because I want you to imagine this situation. One day an alien friend texts you and says he's coming to visit. Then he asks for directions to your house. Would you know how to answer? I mean, I'm sure you know the street, city, and country where you live, but could you go higher? Do you know where the Earth is in the universe? Don't worry, I'll help you out. Earth is the third planet orbiting the stars we call the Sun. The Sun is one of the billions of stars that make up our galaxy, the Milky Way. It's a spiral galaxy, which means we can distinguish two basic areas: the historic quarter, the bulge, where the oldest stars live alongside a gigantic black hole, and the modern part, the disk, filled with lighter elements, the perfect place for new stars to form. This is our neighborhood. Specifically, the Sun lies on one of the spiral arms, called the local arm or Orion arm, Or maybe not. Astrophysicists are debating whether the Orion arm is just like the rest or a kind of bridge between the Sagittarius and Perseus arms. Trying to figure out the shape of your galaxy when you only have a side view certainly isn't easy. But let's continue. The Milky Way is one of the 3 largest galaxies in the local group, a club that also includes Andromeda, the Triangulum Galaxy, and a whole bunch of little galaxies called satellite galaxies which orbit them. If these guys are small villages, then we live in one of the major cities. And in a few million years, our city will be a metropolis because the Milky Way and Andromeda are eventually going to merge. But we're not done yet. The local group and many more galaxies lie inside the Virgo supercluster. Although recent research indicates that we're part of an even larger structure called the Laniakea supercluster. Superclusters are mass concentrations of galaxies, but all around us galaxies are organized in other, far bigger ways, forming filaments or walls and vast voids that are all part of one great cosmic web. In any case, what superclusters have in common is that they're gravitationally linked, which means they will merge at some point. In fact, the entire Laniakea supercluster is headed toward a place where there are lots of galaxies, called the Great Attractor, a deceptively mysterious name. By this point, you're probably thinking this is an endless task that we're always going to find we're inside an even larger structure, give it a name, and add another line to our cosmic address. Well, surprise, we won't. Once the galaxies are grouped in this web, the universe looks the same in every direction. On the largest scales, the cosmos has a uniform appearance, and matter looks evenly distributed. In other words, from this perspective, there's no way to statistically distinguish one part of the universe from another, so we can't assign it a physical address. In summary, our address is the Earth, Solar System, Orion Arm, Milky Way, Local Group, Virgo Supercluster, Laniakea Supercluster. Zip code? Well, never mind. The thing is that this property, the fact that at a large scale the universe looks the same everywhere, in other words, it's homogeneous and isotropic.
So you get the idea that the universe is really big. Okay. When I first started studying this, they were saying Earth is 4.5 billion years old, and the known universe is 13 billion years old. And that has to do with the farthest away stars that can be detected and deduced from a means where they have a certain type of star. It's a pulsar that only exists in a fairly narrow size range. It can't be much bigger, it can't be much smaller, or it will not pulse. And so if you look at the brightness on pulsars, you can therefore deduce how far away a pulsar is based on the brightness of that light. And so that, combined with parallax on the closer galaxies, when we're on the opposite sides of our solar orbit around the sun, it forms a triangle, so we get a little bit of parallax for the closer galaxies, but the farther away ones, you can't do that, they're too far. So you have to use some other kind of estimation. So they came up with 13 billion years. Well, now with the Webb telescope, we're finding stuff even farther away. And so now the latest estimate I've seen is something like 26 billion. But then if the light is coming from 26 billion light years away, it had to be there, had to get there somehow, and then come to us, which means it's probably more like 92 billion. I mean, the numbers they're complete guesses. But they're big. Okay, the universe is huge. And there is every possibility that there is no edge of the universe, that it goes on like this infinitely, because God is infinite. So we don't know how big the universe is. We are, interestingly enough, on about 2/3 of the way out in the Milky Way galaxy. And we are on what they believe to be one of those spiral arms, but we're toward the edge of it. What this does for us is it makes it a perfect position for observing. We are close enough to the edge of the spiral galaxy itself that we can see outside the galaxy. If we were too far into the galaxy, we'd be inundated with light. We couldn't see anything beyond the galaxy. It would be like light pollution every night just from the stars. But we're far enough out that we can actually see outside of our galaxy. This is a really lucky thing, right? what if God designed our position and designed us so that we could observe and see as much as we can about his creation? That's the argument of a book called Privileged Planet, which is a really good read on how these factors come together to make us perfect for observing. We have optimal light sensors called our eyes. We have a perfect position, and we're protected being inside, not quite at the edge of the galaxy, but we're inside far enough that we get some protection from rogue space debris. And that happens within our solar system as well. We'll talk about that. So we're protected, we're in a good position to observe, and we have the capability of observing. Again, finely tuned to observe what God has done. I'm going to show two videos next about how planets form, because we're going to turn our attention now on the solar system. The first one is going to be how they characterize it for adults. And then we'll see how they characterize it for kids. And I think you'll see the adult one is a little more circumspect. It has a little bit more, well, we don't know for sure kind of language. The kids one, not so much. So let's do it.
How did planets like Earth first form? That story starts 4.6 billion years ago with the birth of our solar system. As a vast cloud of dust and gas collapses in on itself, pressures increase, temperatures at the center rise to millions of degrees, until energy from the early sun blasts away some of the cloud. This lights up the young solar system, revealing the beginnings of planets. The mystery has always been, how did this spinning cloud of dust become the massive planets we see today?
How does one go from microscopic grains to golf ball sized things? And how do golf ball sized things go from there to 10-meter sized things? And how do those go to planetary embryos? And there's a lot of steps in there we don't quite understand.
Many scientists believe the answers are hidden in asteroids, the oldest rocks in the solar system, leftover debris from its earliest days.
Asteroids are just not lumps of rock. These are the basic parts or building blocks of planets.
Over hundreds of thousands of years, asteroids collide, growing bigger and hotter. As their gravity increases, they attract even more asteroids, until eventually, as temperatures rise, they become spheres of rock with hot, molten cores, protoplanets. Computer simulations suggest that within 10 million years of the solar system's birth, up to 100 protoplanets ranging in size from our moon to Mars were orbiting close to the sun. So why does the solar system look so different today? A protoplanet the size of Mars slams into early Earth. The collision is so violent, it melts the surface, creates an even larger planet, and blasts molten rock back into space that will coalesce and eventually form our moon. Earth isn't the only planet that gets transformed by giant impacts. Over tens of millions of years, all the protoplanets of the early solar system repeatedly collide, becoming larger bodies with each impact. This process eventually formed the 4 rocky planets seen today: Mercury, Venus, Earth, and Mars.
And so the final planets that we have today are really the ones that won the competition, and that some planets were literally destroyed or thrown out of the solar system, and others survived to be here today.
So did you see the waffling kind of language? As in, we don't really know, but they're still pretty confident, right? And you'll see this kind of language, this dualistic, we're really sure it's from NASA, so we must be sure, right? And yet, maybe not. Did you notice how they came up with this data? What was the tool that they used? Computer model. So whatever you program the computer to do, that's what it's going to model. And it's going to have some biases about how that is done. Okay, so this is how they describe it to kids. See if there's a different tone to what happens now.
Orbiting around our sun, we find asteroids, comets and planets with their moons. But how did our solar system form? Around 4.5 billion years ago, a cloud of mostly hydrogen gas and dust started to collapse onto itself. It spun faster and faster, flattening out to form a disk with a dense centre. This centre got so hot, it started making light, and our sun was born. Around our baby sun, there was still a spinning disk of gas and dust. Over time, it cooled and came together due to magnetism and gravity. Close to the sun, metals and rocks began to form, but it was still too hot for other materials to become solid. They remained as gases. Further from the sun, where it was cooler, water and other ices could form. They came together to make larger pieces, called planetesimals, which then joined to make large planets. These planets had enough gravity to capture the surrounding gas and became the gas giants, Jupiter and Saturn. Some scientists think Jupiter formed first and was pulled in towards the sun by the swirling material in the inner disk. When Saturn formed, it moved inwards too. The planets got closer and swept up the gas between them. They then began to journey outwards together. Jupiter's large size stopped rocky material clumping together. The asteroid belt is full of these rocky scraps of the solar system. It might also explain why Mars is smaller than expected. When Jupiter moved inwards, it fed on lots of material, so later Mars had less to form from. In the inner solar system, chunks of metal and rock slowly came together to create the rocky planets. Within 100 million years, early planets were orbiting the sun with lots of leftover material in between. The young sun had a phase of releasing strong winds. It blew the extra gas outwards, stopping the rocky planets and early gas giants from growing. The outwards moving gas was pulled in around the snowball cores of the ice giants Uranus and Neptune in the outer solar system. Many of the leftover ice balls flew out into the spherical Oort cloud. They occasionally got flung inwards, becoming comets, and collided with the rocky planets. Perhaps comets brought ices and gases back to these planets, providing material for their atmospheres, and also bringing water to the Earth. For the first billion years, many stray pieces of rock and ice would have been flying around, creating lots of collisions. The Earth's moon could be the result of a large object impacting the Earth. Similar impacts may have reversed Venus's spin and knocked Uranus onto its side. Some of the planetesimals still floating around were captured by the giant planets to form moons around them. Scientists are looking to distant stars with exoplanets to see how they form. Maybe then we'll know if we truly live on a unique planet in a very special solar system.
It's very cute, and it's the Royal Observatory of Greenwich, so you know it has to be authoritative, right? There is so much wrong with this video. Don't get me started. But they don't understand gravity, they don't understand how orbits work, they don't understand how chemicals work, they don't understand how metals are formed. They're not formed in space where it's cool. I mean, it's formed by fission in stars. Anyway, you just can't explain the universe from this kind of explanation, but they do. And our kids are told this all the time, and it comes from their teachers and authoritative sources. It's the kind of stuff I believed when I was going through school, because that's all I was taught. Well, it turns out there are some other answers, and we're going to look at some of those. So we're going to move to a little more realistic case the solar system case for intelligent design. That's where we'll focus. So we're going to talk a little bit about formation of planets. We'll talk about cosmic cookie dough and how we get spinning tops that we can think about with planets. Orbital mechanics, that's just how orbits work. It's rocket science, but we're not going to use formulas, so don't worry. It's going to be just the ideas involved and not the formulas. And then we may or may not get to very much of this, but the idea of habitable factors and protection is kind of what I talked about at the start, so we won't really get into too much of that. That's kind of a separate case, but we have kind of been there already. So let's look at planetary formation, how the solar system works. We all know that the solar system is made up of, it used to be 9, now it's 8 planets, and they are in orbits. What we don't think about too often is that they're all almost in the same plane, but not quite. And so that's why we don't see planets real close to each other very often, is because the angles have to line up as well as the timing. And so this is the close part of our solar system, and we've all seen pictures of this in the books. And so the question is, how do we get the planets to be the way they are? So let's have a kind of a comparison. If you were going to make chocolate chip cookies, you would have something that has a recipe, and it has things like chocolate chips, okay? Because you're making chocolate chip cookies, you have a recipe. There's a way to make those things, okay? But what if you want to make a different kind of cookie? What's going to happen? You're going to end up with a different recipe and a different set of ingredients. So if you know what the outcome is, you know somebody's going to design a way to get to that desired result. Well, what about the planets? Do we have a recipe for that formation? One of the arguments you heard a couple times is that the planets formed out of a dust cloud, and they gradually clumped together. This process is called accretion. It's like when an ice pellet goes through a rain cloud, gets a little bit bigger, and then the updraft carries it, and it becomes a little larger piece of hail every time it goes up and down. That's accretion. It just gets more and more stuff on the outside. The question is, can we do that in space? Because you have to have a certain amount of mass to have any gravity at all. You have to have some gravity to attract something to yourself. So how are you going to attract this stuff if you're not big enough already? You have to get the first start of a big enough thing to have gravity before you can attract anything to yourself. So are you going to be able to attract to yourself just out of a dust cloud clumping together? And so first of all, if all the planets came out of a common dust cloud, what would they look like? The same. They would look like each other, right? Well, do they look like each other? They really don't. What we would expect is similarity. What we see is that they are different in density. They're different in geology. They're different in atmospheres. One of the things that they like to talk about is because comets have some component of water in their makeup, that's how we got our oceans. Well, looky here, how come the others didn't get oceans? Well, it turns out some did. There's a moon of Jupiter called Europa that's an ice giant, a giant moon with lots of cold water. What about all the other moons of Jupiter? Where did their water go? You could do that over and over with geology, with the gas giant being different from the rocky planets. They're not the same, and if they were to form accidentally, happenstancely, you would get sugar cookies with ice cream, with icing and chocolate chips, but not very many chocolate chips. What's the point of a cookie without chocolate chips, right? But they'd be spread out in all these sugar cookies. What a waste, okay? They would be the same as each other, but they're not. So some scientists realize, well, okay, that's probably not the way it happened. So maybe they were captured. Maybe they were formed in separate places, and then gravity captured them as they went by. And so here's the argument. The planets are so different, they have to have been formed separately, and then wandering aimlessly in space, they were captured by our sun, and their orbits eventually stabilized, Shazam, magic, and they're in the positions we see now. Let's look at how orbits really work. And again, this is going to be conceptual, don't worry, no formulas required. Kepler's laws of planetary motion are these 3 laws. The orbit of each planet is an ellipse with the sun at one focus. The line joining the planet to the sun sweeps out equal areas at equal times. The square of the period of the planet is proportional to the cub's mean distance from the sun. Everybody got that? Okay, let's make those a little more understandable. First of all, if you take a cone, this is a cone that, think about it extending infinitely into space. And these are like straight lines, but they go through a point. You know what a cone is, right? So geometrically, if you take a cone and you cut it, if you cut it vertically so that it does not go all the way across, you get this shape called a parabola. If you cut it across, diagonally, you get an ellipse. Now, if you could be completely perpendicular to the center, you would get a circle, okay? But circles are impossible. You can't get circles. They're too perfect, okay? We don't ever have perfect orbits. So everything that is in space that is being affected by gravity is on what's called a section of a cone or a conic section. It's either a parabola or it's an ellipse. That's it. I think there's a hyperbola in there someplace, but it's going to be a conic section, okay? So in order for orbits to work, these three laws describe how these shapes are formed. So the first one is an ellipse. Anybody remember an ellipse? It's what you get where you have two what we call focal points. And this is an example of drawing a circle or a rounded shape where you have a circle of string. So the distance here is always going to be the same between these 2 points. The sum of this and that will always be the same number. So over here, this string is going to be shorter, this one's going to be longer, but the sum of those two is always going to be the same. That's an ellipse, okay? That's all it is. Every planet, every object that's in orbit is an elliptical orbit. Period, dot, that's simple, right? Okay. The next one that Kepler came up with is, this one is amazing. The line joining the planet to the sun sweeps out equal areas in equal times. Now, we're going to look at what an ellipse is, but how an ellipse works. But when you're closer over here, we'll have some examples of this so we look at some animation. When you're closer to the object, you kind of swing by, and then out here you're going slower. So if this is, let's say, of the moon, and this is 3 days, and this is 3 days, completely notional, the amount of area in here is the same as the amount of area in there. Kepler was an absolute genius. He figured this out on a piece of paper and pencils and calculator and math. No calculators, doing calculations. But it's actually true. So the same amount of time, any part of the ellipse is going to have the same orbit, area inside that shape. Okay, and then the third one, this one's a little bit more complex sounding, but the concept is simple. The square of the period of the planet is proportional to the period. Yeah, okay, let's just look at a picture, okay? All right, so here we have, let's say we have a sun and we have a planet, okay? And we're going to put this planet in orbit in a relatively circular orbit around the sun. All right, and as it goes around, it's going to go on a path where its centrifugal force exactly matches the gravity so that it's stable in this orbit. Now, if we put a planet a little farther out, we're going to have a larger circle that it has to go around, and a larger ellipse, right? And so this one's going to move slower. The way I've drawn these, this is actually twice as slow as that one. That's not a perfect representation, but the idea is the farther out you are, the more time the orbit takes, because out here, your gravity from the sun is less, because gravity, as you go farther out, the gravitational force is less. So the gravity here is less, so this planet has to move at a slower speed to stay in a stable orbit. If you can understand that, don't worry about the square and the cube, but that is the actual relationship. But the farther out it is, the slower the motion is to oppose the gravity that is being experienced by that body. Everybody with me on that? That's all you need to know. You don't have to do the math. Okay. All right, this was 1609. Okay, way back there. Amazing stuff. Just a few years later, 1687, Newton refines some of these laws with his laws of motion. Everybody continues in its state of uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. So it's going to go in a straight line until something changes it. It will not be moved off of that line unless there's some other force. Okay? The rate of change of momentum is proportional to the force impressed and is in the same direction. Billiard balls, right? And then for every action, there's an equal and opposite reaction. Those are refinements of some of the things that Kepler was observing. Okay, so now we're going to do something really dangerous. Everybody get out your phones. Okay, now I sent you a link to this. We're going to play with orbits for a minute. So the QR code should take you, well, let me know when everybody's got the QR code, but it should take you to a website at Colorado, University of Colorado. So here's what it should look like. Okay, so the gravitational force is always going to be toward the center, so I'll make that go away. And you can make the velocity appear and disappear, the path appear and disappear, and the grid appear and disappear. We'll keep the grid up there for right now. So if we start this in motion, it's going to be a satellite that's going to be orbiting the Earth, okay? And it's going to be in a relatively circular elliptical orbit, okay? Now, what we do when we send people to space is we send up a space capsule, and I know this was, I knew more about this in the days of the shuttle when I had a friend who was an astronaut, but he described what would happen is they would put imagine this being the space shuttle, and they would go into a low Earth orbit around 200 miles above the surface. Now the space station is in a 400-mile orbit, so it's higher up. So how do you change orbits? That's a real challenge. And it's actually a very, very complex operation, but we're going to do it with a computer simulation. So if I'm going to get into a higher orbit, I'm going to do this. I'm going to, let me get myself kind of a beam where it's easier to show. So we'll stop right about there. All right. So if I'm going to get in a higher orbit, we're going to do what's called a Hohmann transfer. So I'm going to accelerate a little bit more than I was at the speed, a little more here. And what that's going to do is it's going to take me into an elliptical orbit with a larger distance on this point over here. Okay, so if we continue now my orbit has changed slightly. It's not the circular orbit, now it's elliptical. And you can see also the velocity is faster here, slower when it gets farther away, and the gravitational force is less, and then it kind of falls back toward the low spot where it's accelerating. Okay? But I want to stay in this orbit out here, so how do I do that? Am I ever going to just happen to stay there? I will stay in this orbit until something moves me out of this orbit. So I will always return to the same point as where I started that acceleration. So if I want to stop the orbit that I'm in, and I want to go into that larger orbit, what I have to do is when I'm at the desired orbital height, altitude above the Earth, I have to give myself a little more thrust. So I turn on my rocket motor, accelerate just a little bit. You don't want to do too much or this thing goes way out of whack. And now I'm on a higher orbit, hopefully intercepting the orbit of the space station. And if it's not quite right, I can add or subtract a little bit based on where I point the rocket thrust to accelerate or decelerate. So that is called a Hohmann transfer, where you're in a low orbit, you accelerate on the opposite point or the desired altitude, you give yourself another stabilizing burst. And when you watch Apollo 13 next time, it'll make more sense, because that's what they were doing when they had to do the rocket burn that put them back into Earth orbit and did not allow them to go out beyond the Earth and get slingshotted toward the sun or whatever. So that's how orbits work. Now, if we want to make this a little bit more relevant, let's make it the moon. Okay, and we will kind of reset ourselves. And I'm going to put the moon down here. Now, one of the ideas that we're going to talk about that people think happened is that the moon was dislodged from the Earth by an impact force. We're going to look at the logic of that. Okay. First of all, if the moon was, let's say I'm coming up here and I'm a Mars-sized planet, and I'm going to hit the Earth and dislodge the moon and send it off on its own. Okay? So here's what has to happen. Remember that we said that whatever point you're on with this orbit, it's going to come back to the same point? Okay, so the force has to be exactly right for it to, first of all, hit escape velocity so it gets away from the Earth. Otherwise, what's going to happen is this. Oops. Okay, well, we'll try it again. So we'll give the moon another shot. We'll put it back over here where it's close to the Earth. We'll give it a little more speed this time, and we'll see if it can escape the Earth. It's going to go farther away, going to come back to the same point as it started, and we did it. Okay. So now the moon is in an orbit where it's not going to hit the Earth, although, to be fair, if it had started at the Earth, where's it going to be? Back at the Earth, right? It's going to hit the Earth again, every time. Not just sometimes, every time. So this is a little bit of a fake example. But we made it work. Okay, but then how do we get the moon, and I need to move my grid, I don't know if I can do that. We'll reset it. So I need to get my moon into a relatively spherical orbit, right? Because that's what it is. In fact, the moon's orbit is one of the most perfectly circular orbits known in the solar system. So how did it get into that perfectly circular orbit? And by the way, always facing the Earth. How do you get that out of an impact, an accidental impact, where the first thing that should have happened would have been this? Even if we give the moon a fairly good amount of velocity, it's always going to do the same thing. It's going to come back to the same point as it was. And it might be around the other side, it's still going to hit the Earth. It's got one orbit to stabilize far enough away with a second impulse of some kind to get into an orbit where it doesn't hit the Earth on the first pass. One shot. So there has to be another gravitational source to accelerate it into somehow another orbit, and it's a perfectly spherical orbit. I mean, the odds are simply astronomical. So, so that's kind of how orbits work and what we do with satellites. But try it at home. The link that I sent you in the email does work. So anyway, so if we move along, this was going to be another, if I couldn't get that website to work, I was going to use this slide, so we'll just move past that. So where'd my mouse go? It should be back over here. Okay. So the bottom line is, how reasonable is it that we could have launched the Earth with an impact? The same thing is going to happen with capture. One of the ideas is we should have been able to capture the moon, kind of like you would catch a ball. And so where did that come from? Was it impact? Was it the idea of capture? And how realistic is it that we could have had that kind of a thing happen? Given the way orbits work, if something is passing by, it's not going to get captured. It's going to get slung in a different direction, or it's going to hit the thing that's slinging by, but it's not going to get captured. It takes another impulse to stabilize it in that orbit. Another theory, because that one has some problems, those two have some problems, is the fission theory, where the Earth-Moon system is spinning so fast that the moon spins off. Okay? The problem with that one is, again, the orbit problem, is if it's fast enough that it's going to spin off, if it's spinning that fast, it's going to spin away and come back to the same point as it started. So once again, you have the same problem. You can't get away from the orbits doing what orbits do. So once, assuming that it was spinning fast enough to have a big piece come off, the whole thing would come apart. If it was spinning in an uneven manner and a part of it came off, it would come back to its point of origin. So that doesn't work too well. The other idea is the accretion theory. And this is where it's gathering out of dust, and it would have to look at the same at all the others. And then, of course, the impact theory. So those are and you'll see this in websites all over the place. This idea of the impact theory is the most commonly cited example on websites is, oh, everybody believes this is what happened. And we won't play this whole video, but it's going to show a computer simulation, once again, of the moon doing what the moon cannot do. So you have an object the size of Mars. It's going to hit, and guess what? It's going to spew stuff all over the place, but some of it is going to stabilize a certain distance out where it can't stabilize. And so again, you can find these all over. Feel free to wander the internet and laugh. Ha ha ha, that doesn't work. But they make it look really convincing. Well, interestingly enough, you can find peer-reviewed papers that will tell you that that's not the case. So this one, flaws in the giant impact hypothesis of lunar origin. And so when you look at the key sentence that I pulled out here, that this hypothesis is implausible in its present form because, one, it possesses a low intrinsic dynamical probability. I love how they use more syllables than you need. The collision would have melted and differentiated the Earth, causing geochemical signatures quite different to those actually observed. And three, the collision mechanics caused the moon to be derived mainly from the mantle of the impactor, where basically scientific papers say it doesn't work. But you don't find this kind of disclaimer when you look at the web, and especially if you look for kids' videos. They simply are not going to be this direct in the problems. So let's look at the asteroid belt. The asteroid belt is an area between Mars and Jupiter. So we have the inner three planets. So you've got Mercury, Venus, Earth. Mercury, Venus, Earth, and then Mars, and then Jupiter's out here. The asteroid belt is between Mars and Jupiter. They don't show the farther out planets, which is fine. And so it used to be, when I was first looking at this years ago, they had said, well, this used to be a planet, but there was an impact that split it apart. But I think they realized, well, that would kind of mess up our moon theory, so we can't use that. So now they're saying it's a bunch of rocky clumps that never quite formed a planet because Jupiter kept pulling them apart. And anyway, so they say it's a bunch of planetary debris. And Jupiter swept out farther out and attracted all the stuff that was in its orbit. How does it do that? Because you got stuff over here on this side of the orbit that's not going to be attracted by Jupiter. It's in its own orbit. Remember, everything is free floating. And the other problem is, when we look at these orbits, the Earth, as somebody pointed out earlier, we're spinning on our axis. And we're going 25,000 miles around in 24 hours. That's a little more than 1,000 miles an hour at the equator. We're going really fast. Everybody catch your breath now, okay? Because that's not the half of it. We're going around the sun, and given the circumference of our orbit around the sun in 365 days, we're doing 66,000 miles an hour. So objects that are in these kind of orbits are going really fast. If there's an impact, do you think there's the least possibility, because we're going 66,000 miles an hour, whatever is going to hit us is also going tens of thousands of miles per hour. The idea that could somehow splay off a certain amount of mass that would then congeal together, every one of those little bits is in its own orbit. Remember the parabola? And remember the ellipse? They're all in elliptical orbits. Unless Newton's laws are wrong, they're going to be unperturbed unless another force interferes. And if they're free floating, gravity is not going to be enough to attract something that's going 66,000 miles an hour. Escape velocity for the Earth, for our purposes, so a low Earth orbit is about 17,000 miles an hour. To escape the Earth's velocity, the Earth's gravity takes about 25,000 miles an hour. So the Apollo astronauts were the fastest men on Earth because they escaped Earth's gravity. They had to get to 25,000 miles an hour away from the Earth. Okay, 25,000 miles an hour on that ellipse will take you far enough out that you won't come back. You're now on a parabola. And they had to be aimed towards something like the moon and then slow down so they'd be in that orbit. Really complicated rocket science, okay? So all of these particles that are being flung out when an impact happens are doing those tens of thousands of miles an hour. And they're not going to be attracted by gravity. They're over escape velocity, any way you would define it. So there's another problem with the planetary formation being accidental, and that is all the planets rotate on an axis. If we were all accidentally formed, what would that rotation look like? Same forces, right? The rotations would all be some form of the same. So if the mass is swirling and somehow that imparts to the planets a swirling motion, and there's some truth, I mean, you can make a case for that, you know, like the figure skaters that pull their arms in and go faster. So as the thing comes together, it should be going faster, right? So that has some logical sense to it. But you would expect the direction of rotation would be imparted by the motion of the cloud, right? Well, here's what we see. The rotation is in all different directions. So we have, for example, Mercury, which is only 0.1 degree off of a perfect perpendicular to its orbit. What's the Earth's rotation compared to its orbit around the sun? You know this one. 23 degrees, right? That's why we get our seasons. Tropic of Capricorn, Tropic of Cancer, we're on a 23-degree tilt to our orbit. That's what gives us our seasons. So what about this one? It's completely backwards, 177 degrees. And if you look at some of the others, they're like Uranus. This is the one that they showed the thing where it tips it on its side. Well, if it tipped it on its side and there's nothing to stop it on its side, guess what? It's going to keep rotating that way. I mean, you can't make this stuff up. At any rate, the rotation should also be somewhat coherent with the description that they're giving us for the formation of the planets, but it's not. So how do they do that? That's the big question. What would have caused this different rotation? And I've never seen a good explanation for why this would be the case. So kind of summing up what God would say about this, he said there would be people like this that would try to give us explanations that defy science, that defy empirical evidence, that defy common sense. So in 2 Peter 3:5, he said, "But they deliberately forget that long ago, by God's word, the heavens existed, and the earth was formed out of water and by water." This is a scientific proclamation. It's accurate. It doesn't have a lot of specificity. There's a lot of details left out of that. It's kind of a big picture, but it's accurate. This deliberately forget idea in Revised Standard Version says deliberately ignore. And in the King James, they're willingly ignorant of these things. And we're surrounded by people that are either choosing not to look, or they're oblivious, or just not looking at it because they're not interested in it. They're busy. I get it. But the facts are what they are. There is a curiosity that we can never escape. This is the verse that I usually start the videos with. In Ecclesiastes, "I've seen the burden God has laid on men. He has made everything beautiful in its time. He has set eternity in the hearts of men." We have this intense curiosity about our origins and about our destination. Yet they cannot fathom what God has done from the beginning to the end, Ecclesiastes 3. This idea of they cannot fathom what God has done, I think that means two things. One is we will never be able to scientifically discover it. We don't have the tools. We never will have the tools. The other is, even if God told us, we couldn't comprehend it. It is probably too elegantly simple and yet so complex when you start looking at these quarks and all the way God did orbits are pretty simple conceptually. But for that to work, we need gravity, we need momentum, we need all these fine-tuned laws, the strong and weak force of the nucleus, so the chemistry all those things have to be perfectly balanced in order for these things to work. So the complexity is probably far beyond anything we can imagine. It's the Darwin's black box idea that we looked at when we were looking at biology stuff. The deeper you look, the more complex it becomes. The same is true with chemistry as it is in biology. The deeper you look, the more we don't know about what we know. And in the last video where we were looking at animals, they say that we know less about the surface of the deep oceans than we do about the moon. Honestly speaking, we probably spent more time there because the deep oceans are really hard to get to and hard to do science. We're doing better with deep diving apparatus and so on. They keep discovering new creatures because when we go deeper, we find new stuff. So we have this curiosity, what God's done from the beginning to the end. And this is kind of an encouraging thing. We don't need to know everything. There's a verse in Deuteronomy 29:29 says, "The secret things belong to the Lord, but our God. But the things that are revealed belong to us and to our children forever, that we may follow the words of this law." There's a purpose for us to know what God has made clear to us. And there's other stuff that we won't know. We don't know everything, but we know what we need to know. So this passage in 1 Peter 3 is really helpful. His divine power has granted to us all things that we need to know. And what has he given us? everything we need to know for life and godliness. We don't need to know all the details of creation, but we do need to know some things about how to live wise lives that God commands us to live. And in doing that, we do that through the knowledge of Him. The knowledge of God is the knowledge of how to live in a godly way. And He's granted to us through this means His precious and very great promises. What a privilege we have, that what He has given us, both scientifically and spiritually, is what we need to know. And they're precious to Him. So, therefore, we should make every effort to supplement our faith with virtue, and virtue with knowledge, knowledge with self-control, and this whole list that we have in 1 Peter 3. We should be diligent about trying to do that. And if we do that, then if those things are yours and abound, they keep you from being ineffective and unfruitful. We all want to be unfruitful and we want to be ineffective, right? No, we want to keep from being those things. And God tells us how to do that. And He also says, whoever lacks these things is blind and short-sighted and has forgotten that he was cleansed from his old sins. So let's not be there. We don't have to be there. We can instead take God's advice and look at the things that He's given us for life and godliness. And then this passage, what do we do with all that with respect to the knowledge that we gain about design? But in our hearts, we're supposed to set apart Christ as Lord, first of all, and always be prepared to give a defense for those who call us to account for the hope that is in us, yet do it with gentleness and reverence and great respect for those with whom we're speaking. And when we do that, there's an opportunity to bring someone a little closer to Christ. Well, one more scientific point and then we'll quit. What's happening at the outer limits of the universe? It turns out there's a lot happening at the outer limits of the universe. You've probably heard that the universe is expanding. It has growing pains. Many of us have growing pains, but not those. This is different. Okay. So the universe is expanding and it's accelerating. And that was the big thing that caused Einstein to change his cosmological constant. When he was developing his theory of relativity, he favored the idea of a stable universe, and so he fudged the cosmological constant away from what his math told him it should be, and he made it a number that made the universe stable. Well, Edwin Hubble had been looking at redshift in stars, and the redshift, I won't go into the details, but it shows speed, and it shows that the farther away you look away from us, the faster things are going. And so as they began looking at this data, and they looked at it over time, they realized not only is it faster the farther you look, it's accelerating away from us. Now gravity would tell us it should be coming back, right? Or if it's still going out, it should be slowing its expanse so that it can collapse. But it's expanding and accelerating. And so now what they've determined is if it was not doing that, we would not have a stable universe. So what God did was on the beginning of the earth, the beginning of the universe, He put the universe in place in such a way that by the time man and the living things came about and were on the earth, the universe was stable. Now we don't know what He did to jumpstart the universe, but whatever He did, by the time the 6 days of creation, however you interpret that, at the end of that period, it was stable and it was good. And when man came, it was very good. But without that accelerating and the accelerating expansion, we would not have a stable universe. And so that depiction of the universe being static everywhere, in general terms, that's true. The density of the universe is constant as far as we can detect everywhere we look. They've now pointed Hubble and now James Webb at some of the darker spots in the sky, and they're looking at all the little points of light, and as they look closer, they realize those aren't points of light. Those are galaxies. It just boggles the mind. But the density, as far as we can look, is the same. God is pointing to the fact that His creation, the heavens declare the glory of God, what He's done. So that's where we're going to leave it for tonight. We have plenty of time for questions, but I hope I haven't stressed your brains too much. Mine was stressed thinking about this stuff. But God is to be glorified in all of this. So let me pray for us, and if you have any questions, like I say, I'll hang around or we can ask in the group as well. So thank you, Lord, that You are a God that is beyond comprehension. You're a God that's so big we can't begin to comprehend, but we can begin to appreciate. Thank you that the empirical science, the evidential stuff that we can look at, gives proof that you are who you say you are, that the word's description, the Bible's description of what you did is accurate, is trustworthy, reliable, and we can live according to your guidance for life and godliness, not just for knowledge about your creation. So thank you for all of that, Lord. We thank you for our time tonight, and we praise you in Jesus' name. Amen. So next week is systems engineering. It's going to be a completely different way to look at evidence for creation. Just in the last couple of years, it's a fascinating approach. How would an engineer design the universe? And then we apply those things to what we see in the universe. And once again, it's another way of looking at the problem and proving that it has to be a designer. So with that, any questions?
Now, why is Pluto not a planet?
Yeah, I think it has to do with the orbit is highly elliptical, and it actually goes inside the orbit of Neptune at some point. So it's not completely in its own orbit. That's the last description I've heard of why. And it's a smaller planet than most. I don't know exactly the size proportion. I decided not to put some of that data in here, but that's what I understand, is it's a little too small and it doesn't have its own space.
It's bigger than our moon.
It's sharing it apart. Yes, it is. Yeah. What else? Anybody else have any other data on Pluto? That's my understanding.
What's it called? There's stuff outside there. Is that the Kuiper Belt? What's it?
There is a Kuiper Belt, yeah.
Outside.
And that's stuff that is loosely distributed outside the orbits of the planets.
Do you think Pluto's kind of part of that? Is what
Well, they think it may have come out of that, but again, with the orbits, the way orbits work, it's where it is, you know. So there may be another planet similar, or another entity similar in size to Pluto that's in that Kuiper Belt. Yeah. Is that what you're referring to? I don't know any detail on that, but yeah. And that's cool too. Again, something I didn't go into, but the Kuiper Belt, as well as the asteroid belt, protect the Earth. Because there's all that stuff out there, it kind of has to make it through the vacuum cleaners of Saturn and Jupiter to get to the Earth, and it has to get through the asteroid belt. And so a lot of stuff that might get to Earth otherwise is trapped or in collisions in the asteroid belt or the Kuiper Belt. Or of course, comets that are floating through the cosmos and get into the range of gravity of our sun, they're either slung back out, and it's such a big solar system that's very low probability that it would hit a planet, or they are sucked into the sun itself. We have seen at least one comet strike. Was it Neptune, or was it? I forgot which one it was. But there was a comet just in the last couple of years that was a big deal. They did photographic analysis and were able to determine some of the elements that were spewed out based on the collision. Kind of cool stuff. What else? The thing about comets and water has always been kind of laughable to me. You know, the fact that comets have water, therefore that's why we got our oceans. Like, you know how many comets that would take to make an ocean? But people buy this stuff. All right, well, if you have further questions, you're dismissed. Go take a nap. You've earned it. And thank you so much for your time. God bless you.